So for this presentation, we are going to be talking about location and direction. So first off, we'll discuss angles, and I figure we'll frame this out in terms of CAD. If you were to go into the units portion of CAD, so when you're in your model space, you just type in units, you'll see that they offer 5 different types of angles. You got decimal, you got degrees, minutes, seconds, gradients, which is like a French version of angles, radians, and surveyor's units. Since I'm sure you're all well versed in terms of decimal, like if I were to say 45.8 degrees, you kind of know what that means. We're going to start with degrees, minutes, and seconds. So I believe you should have talked about degrees, minutes, and seconds in surveying, but if you have not yet, we're still going to cover it a little bit. So when we're using degrees, minutes, and seconds, a circle is from 0 degrees to 360 degrees. And in terms of equivalent units of measure, 1 degree is equivalent to 60 minutes, which is equivalent to 3,600 seconds. So the minutes and seconds are kind of the decimal portion of a decimal degree. So if we wanted to convert degrees, minutes, and seconds to decimal degrees, it's fairly straightforward, which is shown here. So you got your degree, which is going to be your 40. That's going to stay on the left side. Then we're going to do the minutes. So for that, we're going to do 20 divided by 60, because if we remember in this slide, 1 degree equals 60 minutes. So 20 divided by 60. And then we're going to add to that 50 divided by 3,600, because again, previous slide, 1 degree is equivalent to 3,600 seconds. So all you're going to do is add that across, 40 plus 20 divided by 60 plus 50 divided by 3,600, and you'll be given that answer as a decimal degree. Now, if we wanted to do the reverse, it's still straightforward. It just takes several more steps. So for this, the stuff to the left of the decimal point is going to be your degree. So we'll get rid of that. We got 40 degrees. So now we got to deal with that 0.34722 number. We're going to go the opposite way. So 0.34722 times 60, we are given that 20.8332 number. So similar to what we did with to the left of the decimal thing, that's going to be our minutes. So currently we have 40 degrees and 20 minutes, and we're left with the right side of the decimal point, which is 0.8332, and we're going to times that again by 60, because 60 times 60 is 3,600. So when you do that, you're given 49.99 seconds, which is roughly equivalent to 50. It's just rounding errors, and you're given 40 degrees, 20 minutes, 50 seconds. So you can see both of these are equivalent. Degrees, minutes, and seconds are used a lot in conjunction with either azimuths or bearings. And if you wanted to insert bearings in the CAD, when you type in units, you just change the angle type to surveying, which you will use for your site plan assignment. An azimuth is an angle that is measured from 0 to 360 degrees from north or south, and it typically goes clockwise starting from north. That's how I've typically seen it done. Bearings are measured in 90-degree quadrants. So you can break it up northeast, southwest, and your top right quadrant would be the northeast quadrant. Your bottom right would be southeast, so on and so forth. And the way that starts is if it says north some angle, so say it says north 50 degrees, okay, we're going 50 degrees. Are we going east or west? North 50 degrees east. Okay, we went that way, and that's how it works. So if you're looking at that line down here, that's what's happening. Start north, which way are we going? You could do the same thing with any of these, but the first letter is either going to be an N or an S for north or south. The second letter is going to be an E or a W for east or west. And the main thing to take away from that as well is bearings are only in 90-degree quadrants. It's implied, but I didn't explicitly say it. So you couldn't have a bearing that says, say, north 107 degrees. It would have to be less than 90. or 90 or less. Bearings are used a lot in site plans or in terms of your assignment where you have all those plats. You've seen this picture before since it's your assignment, but I recreated it in CAD from a site plan. And you could see all the angles in this assignment are given in terms of bearings. So you got that north or south direction, some degrees, minutes, seconds, and then an east or west direction. So say we wanted to calculate the angle between two bearings. The way you would do this is similar to how you would calculate between time intervals. So the first example is straightforward. You just subtract the minutes from the minutes and the degrees from the degrees, and you get 6230. So you'll do 95 minus 33 will give you 62 degrees, and the 50 minutes minus the 20 minutes will give you 30 seconds. So you got 62 degrees, 30 minutes. The issue is sort of like time or subtracting in some points where you borrow from a certain place. So say you were given the angle between 95 degrees 10 minutes and 33 degrees 20 minutes. When we do the 10 minus 20, that's going to end up as a negative number. So we have to borrow 60 minutes from the degrees. So we're going to be left with 10 plus 60 because we borrowed that degree minus 20. So we have 50 minutes. And then for our degrees, we have 95 minus 1, since we gave it to the minutes, minus 33. So our answer will be 61 degrees, 50 minutes. If you wanted to calculate the external angle, so this previous one was the internal angle, you're given the two and you want to calculate that angle. If you have to calculate the external angle, you do the exact same process as the previous slide, except then that'll get subtracted from 360 degrees, 0 minutes, since a circle is 360 degrees, and we want the external angle. So in terms of this, if we were getting the external angle between 65 degrees, 10 minutes, and 34 degrees, 20 minutes, we're going to do 360 minus the difference between the 65 degrees, 10 minutes, and the 34 degrees, 20 minutes. So if you do that intermediate step, we're going to do 360 minus 30 degrees, 50 minutes, which we're left with an external angle of 329 degrees, 10 minutes. So if we're talking more in terms of a global scale, when we're talking about Earth, we tend to refer to locations and directions in terms of latitude and longitude. Latitudes are the imaginary lines that circle parallel to the equator. So they're those ones. They run from 0 degrees to 90 degrees north and south. And in terms of units, 1 degree of latitude is approximately equal to 69 miles on the Earth's surface. Longitude passes from pole to pole, which are also called meridians. Longitude runs from 0 to 180, east or west. The distance between each degree of longitude is dependent on the latitude. So the distance between each degree of longitude is roughly 69 miles, which is the same thing as before, except that's then multiplied by the cosine of the latitude degree. So 69 times cosine of the latitude. So if we were given two different points, this point A and point B, we could calculate the distance between these 2 points. So point A is 40 degrees north, 15 degrees east. Point B is 45 degrees north, 30 degrees east. We want to calculate that distance. So we are going to get a vertical component and a horizontal component, and we're essentially going to treat it like a triangle where we use the Pythagorean theorem to figure it out. So our vertical component, since we're dealing with the latitudes, we have a difference between 45 degrees and 40 degrees. So that's 5 degrees times 69 miles. That's going to be 345 miles. Horizontal distance, we're going to have the two different longitudes, 15 degrees to 30 degrees. Now what we do here is we take the average of the latitudes. So we're going to take this at a latitude of 42.5 because 45, the average of 40 and 45 is 42.5. So with this, we have 15 degrees, 30 minus 15, times 69 miles, times the cosine of 42.5. And that gives you 763 miles. So then if we just do a squared plus b squared, the square root of that, the distance between those 2 points is 837 miles. Now, there's a way for calculating longer distances, but that's kind of outside the scope of this class, so I'm not even going to bother. When talking about location and direction, it has to be based on something. So generally we use north as something to judge things on. But the question is, where exactly is north? There are 3 different types of north that we could be referring to: true north, magnetic north, and grid north. True north is the geographical north, or the direction of the North Pole. Magnetic north is where, if you pulled out a compass, where that actually points to, which is approximately 1,000 miles away from true north. Grid north kind of splits the difference between those 2 norths, and it's used to indicate the difference between grid lines on map and the true north. When dealing with true north and magnetic north, you will likely talk about magnetic declination, which is the angle between these 2 norths. And it's reported in degrees and mils. And for reference, 1 mil is equal to 1 divided by 6,400 circumference of a circle. So 17.74 mils is approximately equal to a degree. And this is always reported east to west. So you can see that on that image there. If you're in the field or trying to find your way about, you'll likely end up using a topographic map, and this declination will be printed on the map. So you will need to transfer this information to your compass before you take the field. If you fail to do this, any readings you get from your compass will be in error. You may end up very far away. I don't deal with this stuff. I would end up getting lost and probably die, so I'm glad I don't have to deal with that. But just as a point of reference, that's what you're supposed to do. And there are various points that are known locations. So when talking about known points, we have benchmarks, which are permanent markers. And with these benchmarks, you know the exact location, the latitude, the longitude, the elevation above mean sea levels. These are set by surveyors, and they each have an ID number. They're this big plate, and you could contact the USGS or the NCGS to get this locations. Surveyors can also establish temporary benchmarks, which I use in like my work since we do construction. And a surveyor could essentially say, I'm going to call this elevation right here 58 feet. So when you're doing the difference in your construction, if you know you have to demolish something down 30 feet, you know that you need to get to an elevation of 28 feet, or that elevation will be 28 feet because 58 minus 30. And then you work your way up to what you need to do. And you can do this for stationing too. So you may see a whole bunch of wooden stakes out in the field, and those are generally doing stations. So it's like each stake is 100 feet, and it's like this is station 0 plus 0, 0. This is station 1 plus 0, 0, 2 plus 0, 0. So it's 100, 200, 300. So surveyors will also come out and establish temporary benchmarks that could be used for construction projects or whatever else. I included this picture in here because Rowan likes to use it a lot. One of these teachers is photoshopped into this picture, which always amuses me. And then also, if you're checking out the background, because that guy in the front's Henry Rowan, if you check out of the background, you got student Chris just derping it up. So I like to include that sometimes. Here's references. That is the end of this presentation. And that's the end of all of my presentations, actually. So the last presentations will end up being all the ones you guys gives, in addition to my demos.